Avogadro's number, and the mole. So last class we talked about counting units. In particular, we worked with the counting unit of 1 dozen. We used a dozen to group M&Ms to essentially make counting a large number of them easier. Today, what we're going to be looking at is a counting unit that allows us to work with atoms. Okay? So last class we established that 1 dozen objects, 1 dozen things, equals 12 objects or 12 things. So 1 dozen of something is 12 of something, right? And we established that because 1 dozen is a way to group objects, we can refer to it as a counting unit. So if we think about eggs, rather than having to count out 144 individual eggs, a lot of times what we do is we'd say, oh, I have 12 dozen eggs. It's just a way to group things to make counting simpler. In chemistry, the thing that we need to spend the most time counting is typically atoms. Now, ideally, we need a counting unit that allows us to group atoms and make it easy to keep track of them. Unfortunately, a dozen doesn't really make sense to use as a counting unit for atoms, and the reason is because atoms are simply too small. So what that means is that we need a counting unit that is essentially made to accommodate a larger number of objects, way more than 12, for example. So in chemistry, what we use as a counting unit is called the mole. Okay? And what we say is we say that 1 mole of objects is equal to 602 sextillion objects. So I'm going to write that number out because that's a big one. 602, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 602 sextillion objects. Now, that's an enormous number, right? It's probably the biggest number you've ever seen. But that's okay, because guess what? Atoms are really, really, really small, which means that we need to have a super large group of them in order for it to be something that's meaningful to meaningful to the visible eye. Now, let's go a little bit more in depth. Let's look at this. We're going to be working with this number a lot. If you remember last time, we used 1 dozen equals 12 as a conversion factor. Similarly, we're going to be using 1 mole equaling 602 sextillion as a conversion factor. Now, it took me a little while to write this number out, so we want to be able to write it more conveniently, which is where scientific notation comes in. So what you'll more frequently see is that 1 mole is equal to 6.02 times 10 to the 23rd things, whatever it is that you're counting. All I did here, right, was just put this number in scientific notation. So we're essentially just moving the decimal. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay? This expression right here, 1 mole equals 6.02 times 10 to the 23rd. And in particular, this number is what we call Avogadro's number. And Avogadro's number is really important because Avogadro's number tells us the number of particles in a mole. So I'm going to say that one more time. Avogadro's number, which is 6.02 times 10 to the 23rd, tells us the number of particles in a mole. Just like 12 tells us the number of objects in a dozen. So let's take a minute and think about this. Really, the take-home point here is that 1 mole of anything, like literally anything, actually anything, equals 6.02 times 10 to the 23rd of that thing. Okay? Just like 1 dozen of anything equals 12 of that thing. So let's take a minute to think about this. I think that we're all really comfortable saying something like, okay, 1 dozen eggs equals 12 eggs. Now, just like 1 dozen eggs equals 12 eggs, 1 mole of eggs equals 6.02 times 10 to the 23rd eggs. Now, the only difference really is that a dozen is 12, whereas a mole is 6.02 times 10 to the 23rd. A mole's quite a bit larger than a dozen. Similarly, 1 mole of, I don't know, basketballs equals 6.02 times 10 to the 23rd basketballs. Now in chemistry, the reason the mole is so important, and really the whole point of this, is that because the mole accounts for such a large number of objects, it's what we use to count atoms. So the way that we will most often talk about a mole is to say that 1 mole of atoms equals 6.02 times 10 to the 23rd atoms. Okay? 1 mole of atoms equals 6.02 times 10 to the 23rd atoms. So essentially, the mole allows us to convert back and forth between moles and atoms. Let's think about a few concrete examples. Okay? Let's consider 1 mole of carbon. In 1 mole of carbon, there are 6.02 times 10 to the 23rd atoms of carbon. Similarly, in 1 mole of, say, gold, there are 6.02 times 10 to the 23rd atoms of gold. Now, what about in 1 mole of water molecules? Guess what? In 1 mole of water molecules, there are 6.02 times 10 to the 23rd molecules of water. Okay, so these are all examples of what we already know, which is that 1 mole of anything contains 6.02 times 10 to the 23rd of that thing. Now, what if I wanted to start working with something other than just 1 mole? What if I wanted to work with 2 moles or 3 moles, or what if I wanted to work with half a mole? Let's look at an example to see how this really starts to become useful. What if I want to know how many atoms of silver are there in 5.7 moles of silver? Well, now is where I want to set up my dimensional analysis. So, as always, I'm going to start with what I'm given. In this case, it's 5.7 moles of silver. Now, if we pause to think about this, or if we map it out, hopefully we can recognize that we're given moles and we're trying to go to atoms. As I set up my conversion factor, what I want to recognize is that I have moles of silver up top here, which means that regardless of whatever else happens, moles of silver has to go on the bottom here. I'm trying to get to atoms, which means that I want to put atoms of silver up top. Now, if I think to what I know about Avogadro's number, or in this case, what I know about a mole of anything, I know that a true relationship is that in 1 mole, there will always be 6.02 times 10 to the 23rd atoms. Checking my units, they cancel, which means all that's left is to do my math. Doing this out on the calculator can be a little bit tricky. I can show you right here. Let me actually grab a calculator. It's going to be difficult for you guys to see the screen, but what I can do is show you how I would enter it. So essentially what we're going to do is I would enter in 5.7, okay, just the way you would a normal number. We're going to multiply that. Then what you want to do is you want to open a parenthesis. So I'll draw it as if the buttons you would press. You're going to open a parenthesis. You're going to put in 6.02. Okay. Then what you need to hit is, do you see this yellow second button? I know it's kind of blurry because of the height of the camera. Okay, but it says second on it. Second. Then you're going to actually hit the comma button, and I know it's blurry again, but if you can see, there's a little yellow EE. Okay, so you're going to hit the second button, then the comma button that has a small EE above it, and then you need to enter your exponent, which for us is 23. You're then going to go ahead and close off that parenthesis and hit enter. So when you hit, what this will look like in your calculator when you enter it, it'll look just like this, 5.7.02, and then you'll see an E 23. So if it looks like this, you've entered it correctly into your calculator. Okay, hitting enter will give you your answer. When you hit enter, your answer should come out to be 3.4 times 10 to the 24th atoms of silver. Now, when you guys hit enter on your calculator, it may give you the number looking like this, 3.4 E24. Your E simply is like the calculator's way of saying times 10. Okay, and then the 24 is your exponent. So that's exactly the same as writing 3.4 times 10 to the 24th. We like to write it this way when we report our answers because we're humans, not calculators. Okay, so getting back to this, here's our answer. We'll notice that our units cancel, and we're left with the units we're looking for. Conceptually, you can pause here and ask yourself a question. So we know that 1 mole of anything contains 6.02 times 10 to the 23rd of that thing, right? That's what we initially learned right here. 1 mole of atoms is 6.02 times 10 to the 23rd atoms. Because I'm starting with 5.7 moles, I should know in my head that I'm expecting my answer to be larger than 6.02 times 10 to the 23rd. And if you look, it is. So that's a good conceptual check that you can do. All right, let's go ahead and look at a second example. We want to know how many moles of platinum are there in 5.39 times 10 to the 24 atoms of platinum. So you'll notice this time when we set up our conversion, we are in fact starting with atoms, and we're being asked to find moles. Luckily, this relationship, we know, still will involve Avogadro's number. So I'd like to start with what I'm given, right, which is 5.39 times 10 to the 24th atoms of platinum. Now, even if I don't know anything else, I do know that whatever I have here needs to go on the bottom. So I know that atoms of platinum needs to go on the bottom. I'm trying to reach moles, which means that moles will go on top. Using Avogadro's number, I know that it's true that 1 mole of anything, in this case platinum, contains 6.02 times 10 to the 23rd of that thing. In this case, it's atoms of platinum. Now, checking my units will cancel out. I'm going to pause here before I do the math. And again, we're going to go back to that conceptual check. We know that 1 mole contains 6.02 times 10 to the 23rd atoms. We also can see that this number right here is larger than 6.02 times 10 to the 23rd atoms, which means that we are expecting our answer to contain greater than 1 mole. That's a good way to check to make sure that you set your problem up right, as well as that your math is correct. Now, to do this math, we're going to need to enter it into our calculator, right? So we'll have 5.39 times 10 to the 24th divided by 6.02 times 10 to the 23rd. Again, for those of you using the graphing calculator, it will look like this, or it should look like this once it's entered. 5.39 E24 divided by 6.02 E23. Okay? Your answer should be greater than 1 mole. When you do this out, hopefully you'll find that your answer comes out to be 8.95 moles of platinum. Now, To summarize this, after those two examples, we've kind of learned a powerful tool today because what we've learned is essentially how to convert between moles and atoms. Moles and atoms. We learned that we can do this using Avogadro's number always, right? That's the key. Now, if we're starting with moles and we're going with atoms, every single time our conversion factor should be moles on the bottom and atoms up top. Because Avogadro's number never changes, it's always 1 mole to 6.02 times 10 to the 23rd atoms. If we're going the other way, we're starting with atoms and going to moles. Now our conversion factor will be flipped. We'll need atoms on the bottom and 1 mole up top. Again, we know that 1 mole contains 6.02 times 10 to the 23rd atoms. And this right here is very important because it is the start of what you will see and learn to love as our mole map.